Hello, everybody. Welcome to the Herb Yasak Memorial Lecture Theatre we built online, especially for the purposes of COVID. Every year, I do one training seminar as a part of the OpenFOAM Workshop. And this year, as a wish of Professor Philip Cardiff, we are going to talk about the finite volume discretization with polyhedral cell support. Since I've been playing the OpenFOAM game from the beginning, I am going to write out the basis of finite volume discretization exactly in the manner that it is implemented in OpenFOAM. So we will first start by describing the discretization of computational mesh, which is drawn up here behind me. And then we will discretize a standard transport equation for a passive scalar called phi. The form of the equation is as follows. d phi by dt plus div u phi minus div gamma grad phi equals s of phi. In this equation, d phi by dt is my rate of change term. It contains inertial effects, and it basically tells phi to stay where it is unless something else is happening in the system. The term on the right-hand side, I will refer to as a volumetric source or sink term. If there is a source or sink of phi locally, it will interact with the rate of change term to change it. The other two terms are transport terms. The first one on the left-hand side is the convection term, which basically represents a coordinate transformation. It is the way that material moves from one point to another point, carried by the velocity field. The final term on the left-hand side is the diffusion term. It is also referred to as gradient transport, and it will move phi from the region where the values are high towards the region where the values are low. The two properties that follow with this equation is u, which is my convecting velocity, and gamma, which is my diffusivity. Please note that phi, u, and gamma, as well as s of phi, are fields. For example, the velocity field will contain the value of the velocity vector as a global Cartesian xyz vector for every point in space and every point in time. So I can write it as a function of x, location, and t, time. The first step in the discretization is to describe the computational domain to my computer. And I will do that in the finite volume method using a computational mesh. Behind me, there are two types of computational meshes that I use on a regular basis. The first one is a Cartesian mesh, and the second one is a two-dimensional, unstructured triangular mesh. The bits that you need to notice here is that the mesh contains of a set of control volumes. Let me mark one of them. For example, this one here, or that one here, where control volumes are separated from each other by internal mesh faces. Apart from the internal mesh faces, which appear between two control volumes, there is a set of faces on the outside surface of my computational domain. Here, I have the shape of my airfoil and the shape of the far field, whereas on the top, I have the outside boundary of my computational domain. So let us get over the first obstacle in the way that we are going to solve the partial differential equation. And that is to describe how the variable phi which exists everywhere in my computational domain, changes in space. You will notice that the computational mesh contains a number of control volumes which do not overlap each other and which completely fill the computational domain. I will describe my variable phi, which exists everywhere, in the following form. Phi of x and t will be described as a value 5p plus x minus xp dot grad phi p, which is a local cell-wise linear function. Its value is carried by the value in the location of the computational points. So coming back into my mesh, for the Cartesian mesh, I will locate the computational points in the centroid of all cells, and I will number them in a convenient manner. To save my sanity on Cartesian meshes, I will start by numbering cells, centers as 0, 1, 2, 3, 4, 5, 6, etc., until we get to the end of the list. Notice two things. As a good C programmer, I have started counting the cells from 0. In Fortran, you would probably start with 1. And I have numbered them in a special way, row by row, column by column. This is traditional. It also helps me, but it does not translate to my triangular computational mesh. In fact, the order of numbering of cells is completely arbitrary. So down here, I can do something like 0, 1, 2, 3, 4, etc. in any order that I like. So what does my solution look like? Well, it will be a set of values of my variable phi for each of the centers of the computational mesh. So I'm going to have my phi for the cells 0, 1, 2, 3, 4, 5, 6, 7 to the number of cells in the computational domain. This thing here, I'm going to refer to as a solution vector. Okay. Based on the solution vector, I can pick an arbitrary point in space in my computational mesh, for example here, and calculate the value of phi at this location as phi of 8 plus x minus the center of cell 8 dot grad phi of 8. This one we will save for later because it just describes a linear variation. We also said that my function phi is a function not only of space, but also of time. So for each instance in time, for example, t equals 0, t equals delta t, t equals 2 delta t, etc. until t equals t. And I'm going to have one set of values of the solution vector. Clearly, the first one at the start of my simulation represents the initial value. Apart from this, on the outside faces, I am also going to have some additional computational points, which will be located on the centroids of those faces. Here, not only will I carry the value of the solution, but I will also carry some information about the behavior of the solution. I can therefore implement a Dirichlet boundary condition specifying the value of phi on all the faces of this patch, a Neumann or some other more complicated boundary conditions like symmetry planes, or indeed coupled cyclic boundary condition. So this describes the machinery of storing the solution, advancing it in time, and relating the solution vector with the location in space. If I just give you a set of values of phi, you would not be able to perform this linear interpolation because each value needs to be associated with the location of the cell center of the appropriate cell by its ordering in the list. Having assembled all the necessary components, let us now consider the equation that we are trying to solve. d phi by dt plus d v of phi minus div gamma grad phi equals s of phi, where phi is described as a discrete function through a set of values that are being provided. What I need to do is propagate the solution starting from the initial value until the end value, such as the value of phi is calculated with respect to the information that I have. The information will be the geometric information, cell volumes, face areas, etc. Connectivity information, saying which cell is connected to which neighbors. And finally, boundary condition information, which describes the interaction of my computational domain with the rest of the universe. How will I perform that? In the case of OpenFOAM, we use the implicit method. The implicit method looks to convert the partial differential equation, which has been discretized in space and time through a set of values, by creating a system of linear algebraic equations, A x equals B, where x is the set of values or the solution vector belonging to a particular time step. A is the matrix corresponding to the system of equations. And for each cell, I'm going to get an algebraic equation of the form AP phi p plus the sum of the neighbors AN phi n equals BP. The finite volume method will perform this discretization by calculating the volume and surface integrals of my equation over the chosen control volume. Here behind my hand, I have two representative shapes of a control volume, say for my volume 8. P will be 8, W will be 7, East will be 9, South will be 3, and North will be 13. And now I can move that stencil through the mesh and repeat the same procedure. For a triangular mesh, I am going to have a triangular control volume, which connects to only 3 neighbors. Our job for the rest of this talk is to convert the partial differential equation into a set of linear algebraic equation, which using mesh matrix and connectivity and the previous solution vector is capable of producing the new solution vector. So let us go through the slides and take a look at some of the basics that we need to do this. Here's my computational cell. You will see that my drawings are slightly simpler than the slide, But in the slide, I have a three-dimensional polyhedral equivalent to what I have drawn. A computational cell will be a piece of space around the computational point P, which is located at its centroid. The definition of the centroid says that the volume integral of x minus xp dv is equal to a zero vector. And that definition applies to an arbitrary shape. Apart from that, I need to be able to describe the individual faces. So one of the tricks within the discretization that I will use regularly is called the Gauss theorem, which allows me to move the volume integral of the divergence operators into a surface integral over the outside surface of the cell. In order to handle that, I need to introduce auxiliary computational points, which are located in face centers, and I will refer to them as F. With each face center, I will have an associated face area vector, SF, pointing outside of the cell of interest, and whose magnitude is equal to the surface area of the face. Notice that the same argument applies to quadrilateral cells, triangular cells, and the polyhedral cells that we're looking at. Having established this, we now need to integrate the partial differential equation in space and time and create the discretized form. In order to perform this volume integral, I need to be able to evaluate the volume integral of my shape function over the control volume. Looking into that a little bit more, the spatial variation that I have specified, phi of x is phi p plus x minus xp dot grad phi p, allows me to evaluate the integral simply as the product of the value of my variable phi at the cell center multiplied by the volume of the cell. This is called a center point theorem, and I'm going to write it out here for future use. So starting with a simple volume integral of phi dv with the shape function that we have prescribed, it can be evaluated as the value in the center multiplied by the volume of the cell. What about the surface integral? The surface integral is evaluated on the circumference of my control volume, and I need to account for ds, which is my unit vector, multiplying the variable of phi. You can see several problems. The first problem is that I have the value in the cell centers, and in order to evaluate the integral over that cell, I need to visit all of the four faces of the cell. Fortunately, I can also postulate linear variation of my function across the face and play the same game. Recognizing that the surface integral is actually a sum, I will separate my sum into integrals over individual faces, and I will evaluate this as the sum over the faces of the face area vector SF multiplied by the value of the variable phi at the face center. Later on, we will talk about how we evaluate SF. Moving on, we need to recognize that the code will operate over the computational mesh, moving my stencil, P in the center, north and south, top and bottom, west and east, right and left, in order to operate in various folds. Here, the issue becomes the ordering of the information. But since we are doing things over the faces, one can recognize that the cells contributing to the discretization of P will only be its first neighbors. Please look into the details of the slides in order to find out how to operate with this software structure. In order to move the development further, let us now consider the evaluation of gradient. If you remember, I said that phi of x at an arbitrary location can be determined by finding out which cell the value falls in, and then performing linear interpolation between the cell center and the cell by multiplying it by the gradient of the cell P. How do we evaluate the gradient? Let us consider a stencil in the Cartesian mesh with points marked as I have them on the screen. Considering that you have the values at the cell centers, how would one be able to evaluate grad phi at the location P? The easy solution, of course, says, well, let's use finite differences. So I can describe the gradient as phi east minus phi west in the x, or if you like, I direction, plus phi north minus phi south in the j direction, where my j vector represents the y direction. In other words, right minus left, top minus bottom gives me a gradient simply by virtue of finite differences. This is excellent for Cartesian meshes, and in fact I have numbered my neighbors in a special way in order to do east minus west as I plus 1 minus I minus 1, and north south as I plus j and I minus j, and it allows me to calculate the values. Of course, I have to divide it by the mesh size, which is delta x and delta y. This doesn't get us very far. The first complication comes if the coordinate system of my east, west, north, south stencil is not aligned with the global Cartesian system. And here I can do some tricks like coordinate transformation. By jumping into a triangular mesh, all of these games become much more difficult. In a triangular mesh, as you can see, there is no such thing as east, west, north, and south, and I can resort to the basic formulation of the Gauss theorem. In order to evaluate the Gauss theorem, in some way, I need to find out the value of phi f. For that purpose, let us consider this face here, pointing northwards. So that would be my SF. I will know phi north, phi p, and the question is, how do I calculate phi f? Quite easy, right? 1/2 of phi north plus 1/2 of phi p will give me the value that I have. And interestingly, the same applies for any type of computational mesh, including the Cartesian, and the polyhedral one that I showed you before. On the slide, you have a slightly more general form, which states phi f equals fx phi p plus 1 minus fx phi n, which takes into account the fact that the cells left and right of the interface may not have the same size. Okay, so fx will be the geometric interpolation factor for a linear function between the two values. Two important messages here. By using a Gauss's theorem, which is in fact a generalized form of my right minus left, top minus bottom finite difference gradient, I can evaluate the gradient on any type of mesh, including triangular, polyhedral, hexahedral, or indeed any other valid mesh. And secondly, in order to assemble the discretization of the surface integral, the cells that appear in the solution vector in connection with my cell P will be the ones with which P shares a face. Let us move a step further and consider how to convert my partial differential equation into the form that satisfies implicit discretization. So the story so far, we have split the computational space or the computational domain into a number of cells and computational time into a number of time steps. From the mesh, we can know the cell centers, the phase centers, cell volumes, phase areas, and interpolation factors that allow us to calculate phi at the phase, knowing the value of phi at the cell center. Secondly, we have created a discrete description of a continuous variable, phi, also applied to u and gamma, which allows me to store the value of the variable at discrete positions in space and expand it to any other positions. We have also generalized the expression for the evaluation of volume and surface integrals. What we will do now is integrate our partial differential equation over the control volume and find expressions that, that connect the value of phi at location of p to all the other values. The easiest one of those is the temporal derivative. Without further ado, writing d phi by dt can be calculated in finite difference terms as phi new minus phi old over delta t, where phi new is our sought solution, which is phi at t equals n delta t, and my phi old is phi of t equals n minus 1 delta t, which is known. So how can we evaluate the temporal derivative from these values? Phi new minus phi old over delta t is simply a finite difference evaluation. We also can introduce higher order interpolation, like the one on the slides, which reads d phi by dt is 3 over 2 phi n minus 2 phi old plus 1/2 phi old, which is basically a parabolic fit through 3 values. My job is to calculate the coefficients that correspond to the equation of the form AP phi p plus sum over the neighbors AN phi n equals BP. But in order to do that, I need to integrate the d phi by dt terms over the volume of my computational cell using the rules that I have given you so far. So that will be phi n minus phi old over delta t multiplied by the volume of cell. Reading this expression, I need to find out everything that multiplies the new value of phi in the cell center and read out the prefactor, which is my AP. So in this case, AP will be Vp over delta t. An will be 0 because I'm not referring to my neighboring cells. And Vp will be Vp phi old at location P over delta t. Note that the sign changes because the term has been moved to the right-hand side. What does that allow me to do? If I write an equation like d phi by dt equals 3, my discretized form will read Vp over delta t phi nu plus 0 equals 3 plus phi p old Vp over delta t. Or if you like, this cancels out, and I'm going to have phi nu equals phi old plus 3 times delta t, because that 3 needs to have Vp built into it already as a result of integrating the right-hand side. So basically, the value of phi n increases the value of phi old by 3, which is my source term, multiplied by the time-step size, and I'm calculating implicitly the new value using the interpolation coefficients. We have done the DDT term and recognized the diagonal and source contribution because it is the easiest one. So let us look into a more complex term. In convection discretization, my term reads as follows. Div u phi, which will be integrated over the volume. Okay. And here u is the velocity field that carries my variable phi through the computational domain. In the first step of the discretization, I will use the Gauss's theorem to convert the volume integral of the divergence into the surface integral. ds dot u phi. Okay? And recognizing that my surface is created as a series of faces, I'm going to convert that into the sum of the face integrals of ds dot u phi, or again, using the central point value, as the sum of the face integrals, integral over SF, SF, I'm sorry, I will lose the integral here. SF dot U times phi F. So what we have here is the dot product of SF and U. So let us consider an arbitrary shaped control volume and the prescribed velocity field that looks like this. For each of the faces, I am also going to have the face area vector. And by convention, the face area vector points outwards of my computational cell. SF.u corresponds to the amount of volume that is fluxed through the face within 1 time steps, and the units are meters per second for velocity multiplied by meters squared for surface, giving me a flux in meters cubed per second. And that is basically a measure of what comes into the control volume and what goes up. Notice that the incoming flux is negative, the outgoing flux is positive, and for the case where there is a 90-degree angle between the face area vector and the velocity, the flux will be 0. The remaining trick is how to calculate phi f, and this is something that we can consider in a 1D situation. So here is my line connecting P and N, where I have the values of phi P and phi N, left and right. And the question I need to answer is, what is the value of phi and an arbitrary location between P and F called the phase center? That's easy. Draw a straight line and write out phi F equals Fx phi P plus 1 minus Fx phi N, where Fx is Fn over Pn, or a geometric interpolation factor. Looking at all of this, we can write a further step in my derivation, which is sum of the face areas, face area vector, multiplying Fx phi P plus 1 minus Fx phi N, and write out the matrix coefficients that correspond to this term. What are they going to be? Remember, my equation reads AP phi P plus sum over the neighbors An phi N equals B. Therefore, my An, sum over the neighbors, is already here. My An will be 1 minus Fx multiplied by SF. And my AP will appear for all of the faces that are shared with the control volume, meaning AP is sum over the neighboring faces, SF, Fx, and finally BP equals 0. What I have written out here is the central difference in convection discretization scheme and the matrix coefficient that belong. Unfortunately, The second order accurate convection discretization scheme is a nice idea, but it suffers from a lack of transportive properties. Notably, you will not know, based on the interpolation that I have written out here, whether the flux goes in one direction or in the other. And in order to preserve boundedness, we need to use other schemes like upwind differencing or nonlinear TVD or NVD family schemes, which will account for the direction of transportedness. Please have a look at the slides for more details. In the meantime, let us press on with our final term in the equation, which is the diffusion term. The diffusion term reads as follows. Divergence, gamma, which is my diffusion coefficient, grad phi, and I will integrate it over the volume as before. And in the first step, I am going to apply the Gauss's theorem to reduce the volume integral to the surface integral. So this is a surface integral on the outside surface of my control volume of ds multiplying gamma grad phi. Dot here corresponds to the dot here in order to allow you what's going on. And I will further recognize that my gamma is a scalar, so I can pull it out here. Also, I can separate the surface integral into the sum of face integrals as before. And I can apply the center point theorem in order to reduce the integral into the evaluation at the face centroid. So what we have here is my gamma f, which is diffusivity. And I have a curious product of the face area vector and the surface normal gradient. So let us jump into a one-dimensional situation where I have a point P, I have a point N, I have a phase between P and N, and I know the values of phi P and phi N. The question is, what is the gradient of my variable phi, of which I know phi P and phi N, in the direction of the face area vector, which is parallel with the P N vector? Well, that's easy. Phi N minus phi P over magnitude Pn, or as I call it in the slides, the F, which is this vector here. Okay. What about gamma? We have two possibilities. In the first one, gamma is constant everywhere. And if it is constant everywhere, then it is given at the face as well. In the second possibility, we have the values of gamma on all the locations in the cell centers, and we need to evaluate gamma here. Well, it's clear, linear interpolation between gamma p and gamma n will allow me to evaluate gamma at the face. So let's put all this together and write out my coefficients. Okay, so that will be the sum over the faces, gamma at the face, magnitude face area over magnitude distance multiplied by phi n and phi p. Therefore, my an coefficient will be equal to gamma f mag s over mag p and my AP coefficient will carry the sum, because P appears in all the faces, of gamma F mag S over mag D. Notice that the expressions are the same. Finally, my BP will be equal to 0. In the slides, you will see more complications that happen on non-orthogonal meshes, meaning in the situation where the vector SF and D are not parallel with each other. What are we going to do about the source and the sink terms? Well, they are really quite easy because they are volume integrated and do not include the neighbors. And that allows us to assemble the matrix from the rate of change, convection, and diffusion operator to create the final expression reading AP phi p plus sum over the neighbors an phi n equals BP for each of the computational cells. We are going to solve this using an implicit algorithm, meaning that the value in the cell 8 will depend on the values in the neighboring cells, which in turn will depend on further neighboring values, creating a system of implicit equations. To round up the story, let us talk a little bit about boundary conditions. In boundary conditions, we will specify the behavior of the variable at the outside boundary. Now, please note, internal faces have got the left and the right cell, which I in the code refer to as the owner and the neighbor cell. Whereas on the boundary, each boundary face is only connected to a single cell. On the boundary face, we have definition of a boundary condition, which can be given either in terms of the value of the variable or the gradient of the variable. So the Dirichlet condition fixes the value of the variable at the boundary, while the generalized Norman condition fixes its gradient. So let us take a look at the example of a Dirichlet boundary condition for the diffusion operator. What I have shown you so far is that the diffusion operator defines SF dot grad phi f as the integrand term over all boundary faces. Therefore, if I pick a cell which is next to a boundary, like this one, for those two faces, I will use the standard discretization procedure as we did so far. Whereas for the final face, I am going to have either the value on the boundary or n dot grad phi f at the boundary. Therefore, my boundary conditions will contribute directly to either the source, meaning BP, or the diagonal term on the matrix. On the slides, you will see that this gradient is evaluated as the value at the boundary minus the value in the cell center divided by the distance, and it's treated in the usual way. So looking at the slide, phi b over mag dB multiplied by gamma f will be a BP contribution, whereas minus phi p over mag dB gamma f will appear in the sum of the diagonal contributions. That brings us to the end of the discretization procedure. And I hope I have shown you that there is no magic allowed. We have played very basic mathematics. We have gone through the volumetric and surface integrals. We have specified and integrated a shape function and created a system of linear algebraic equation which follow the behavior of my original partial differential equation. And quite frankly, this is where the fun starts. So thank you for your attention. I will stop sharing the screen now, and I would be happy to answer any questions. Okay. Feel free to ask your questions in the chat. Okay, well, in case there are no further questions, I think we can stop this session here. Thank you for your time.